So we're going to continue our discussion of optimization problems. And I've got another one here. This is kind of related to what we looked at in some of the previous ones in the last lecture, but it's got a little more information. All right, so let's see what we're talking about. A fence must be built to enclose a rectangular area of 20,000 square feet. Okay, so I have this rectangle. Kind of a sloppy rectangle. Let me try that again. We have a rectangle, and let's call this X and Y. You could call it L and W. I have this thing about not using L, right? It looks too much like a 1 unless you do kind of curly. So let's just call them X and Y. And I know the area has to be 20,000 square feet. So area equals X times Y has to equal 20 and 4 zeros, 20,000. All right, so I know how much the fencing costs. It's $250 per foot for the north-south side and $320 per foot for the other two sides. And I want to find the cost of the least expensive fence. So I'm trying to minimize the cost. So I need a cost function. Right? The cost is 320 times 2y, right? Because there's going to be two sides with that length, the left and right side, plus 250 times 2x, again, because there are two sides with that particular cost, that unit cost. All right, so let me clean this up a little then. This is 6.40y plus 5x. And now I'm going to do what I did in the last ones, right? This is my constraint. And I'm going to use this to eliminate one of the variables in the other equation. Right? So let's see. Let's solve this for y. It doesn't matter, right? You can do either one. Y is 20,000 divided by x. And now we'll substitute that into our cost function. So now the cost is equal to 6.40 times y, which is 20,000 over x plus 5x, right? And let's see. Now we've got a little cleanup to do, right? 6.4 times 20,000, that's 128,000. So this is 128,000 x to the negative first plus 5x, right? And now we can differentiate. C prime negative 128,000 x to the negative second plus 5. And I need to set that equal to 0. And let's solve this for x. Negative 128,000 over x squared equals negative 5. All right, so now let's see. Cross multiply and then divide. So x squared equals 128,000 divided by 5. See, 128,000 divided by 5 is 25,600. And then take the square root of both sides. X is equal to, let's see, the square root of 256,000. That came out nice. X is 160 feet. All right, well, if X is 160 feet, well, wait, there's a step here. And I have a tendency to gloss over this. I think textbooks have a tendency to gloss over this. You really do need to make sure that is a value that's giving you the minimum cost. Right, so let's see. What are our possibilities for X? Well, X, see, this is a little tricky now. What are our limitations on X? X What's its minimum value? Well, see, here it gets a little weird. X doesn't really have a minimum value. X can't be 0. If X is 0, Y is 20,000 divided by 0, and you can't do that, right? So X is going to be, this is going to have to be open here. And what's the maximum value of X? Well, see, this is a little tricky too. X doesn't really have a maximum value. I mean, you may be thinking 20,000, right? But no, X could be 40,000, and then Y would be a half, right? So there really isn't an upper bound either, and that's okay, right? So when that happens, we have to fall back, right? We have to fall back on our rule for finding local extremum, and we just have to do a test, right? I'm going to draw my number line, and I'm going to put 160, and I'm going to pick numbers that are easy to work with. Let's pick 1, and I don't know what's going to be easy on this side, but let's say 200. Right, so now I'm looking at the derivative. Always helps to be sure. Let's not even do it there. Let's do it. No, that was the derivative. Let's do it here. That's the derivative. All right, so when I put 1 in there, I get a negative 128,000 plus 5. Right, that is a huge negative number. Right, so that's negative. And what happens if I put 200 in there? Well, now you're going to have to go to your calculator. It's a negative 128. Whoops, excuse me. Negative 128,000 divided by 200 squared. So that's 4 and 4 zeros. Right, that's 3.2, but it's negative, right? Because that minus sign out in front. So that's negative 3.2 plus 5, which is a positive number. So the function is decreasing and then increasing. So 160 is giving us a minimum. Excellent. That's what I wanted. Okay, but we haven't answered the question yet, though, right? If X is 160, what's Y? If X is 160, then Y is 20,000. Make sure I get the zeros right. 20,000 divided by 160. 20,000 divided by 160, 125. There's your dimensions. The dimensions that give you the required area and that minimize the cost are 160 feet by 125 feet. Okay, so take a look at this one. It's kind of similar. Right, see if you can't work through this one on your own, see what you come up with. All right, so let's see, just reading through here. We're building cylindrical containers. All right, so I'm thinking it's a metal container, so I'm thinking it's going to have a top and a bottom. Just kind of keep that in mind. With a volume of 16 cubic feet. Okay, let's stop there. Right, volume of a cylinder is pi r squared h, and that needs to be 16. Okay, so the top and bottom are made out of a sturdier material. It costs $2 per square foot. And the size is just $1 per square foot. So I need to minimize the cost. Right, minimize the cost. So let's see. What is the cost going to be? Well, the cost is the area of the base. Bases are circles, so that's pi r squared. There are 2 of them, and the cost is, let me show you. Yeah, the cost of the base is $2 per square foot. Plus. Okay. What is the surface area of a cylinder? That one, there's a formula. It's 2 pi r h times the unit cost. Well, that's just 1, so that one actually kind of comes out nice. All right, so let's clean this up a little. This is 4 pi r squared plus 2 pi r h. Okay, now I need to eliminate one of these variables. Which one am I going to do? Well, that means taking that volume formula and solving it for one of these variables. If I try to solve this for r, there's going to be a square root in it. And there's just a single r here. That r doesn't have an exponent. I'm going to have a radical equation. I'm going to have to square both sides, do who knows what. I'd really kind of rather not. Right? I think we're going to keep this a lot simpler if we solve this for h. So h is 16 divided by pi r squared. And let's put that into the equation. Then the cost is 4 pi r squared plus 2 pi r times 16 over pi r squared. Right, now we can do a little cleanup here, right? The pi's cancel, and this r cancels with 1 down here. So this turns into 4 pi r squared plus 2 times the 16, that's 32 r to the negative second. Okay, well that's good, right? Because I'm down to one variable, right? That's really my goal here, right? I now know the cost strictly in terms of r, and I can differentiate this. C prime equals 8 pi r minus 32 times 2, that's 64 r to the negative third. Wait a minute. Oops, sorry. This is that r cancel. This is only r to the negative first. Clean that up. This is negative 32 r to the negative second. There, that's going to be a little easier to work with. Okay, so let's set this equal to 0. Move the 32r to the negative second over. 8 pi r equals 32r. Let me put that in the denominator. 32 over r squared. Now, let's see. Multiply both sides by r squared. 8 pi r cubed equals 32. Divide both sides by 8 pi. R cubed is 32 divided by 8 pi, which is 4 over pi. That's pretty close to 1. But take the cube root of both sides. R is equal to the cube root of 4 over pi, which is 1.084. That's the radius. All right, what were we measuring in here? Look back at the original units. The volume was in cubic feet. Our unit costs were all in feet, so that's going to be 1.084 feet. Okay. Now what? What do we still need? We need to finish the dimensions, so I need h. All right, so come up here. H must be 16 divided by pi times 1.084 squared. Right, you get your calculator out. This comes out to 4.334 feet. Right, so that's the dimensions. Right, the radius of the bases, top and bottom, 1.084 feet, and the height is 4 1/3, give or take. Right, just about 4 1/3 feet. Okay, and we were also asked for the cost. Well, pick the easiest version of the function to work with, right? This is the most simplified version of the cost. So that is the one that I would take 1.084 and substitute into. So the cost is 4 pi 1.084 squared plus 32 divided by 1.084, which comes out to approximately $435.94. 90 cents. That will be your minimum cost. And again, run through the process if you like, right? You can figure, do a number line, right? Check both sides. You can confirm that that does, in fact, give us a minimum cost. Okay, how about this thing, right? Try this one, see what you can come up with. All right, so what are we doing here? We're trying to find the value of theta that maximizes the area of a triangle, right? So let's see. I have this formula, right? Area equals 1/2 AB sine theta. And this sine theta is the only thing that's changing, right? A and B are going to be constants. We're going to let theta change, and I want to find the value of theta that gives us the greatest area. All right, well, let's try this out, right? I'm going to differentiate this thing with respect to theta. I'm actually going to write it because I want to be clear that that's the variable we're differentiating with respect to. So I'm going to actually write this dA d theta equals 1/2 AB cosine theta, right? And then I'm going to set this equal to 0. 1/2 AB cosine theta equals 0. And let's see, multiply both sides by 2 and divide both sides by AB. Cosine theta equals 0. When does that happen? Well, it happens when theta equals pi over 2. Okay, so what is that telling us? Well, I didn't sketch this, but let's sketch this real quick. Theta is the angle between A and B. So I have this triangle here. I have A and I have B and I have theta. And what this is telling me here is that the angle of this the area of this triangle is maximized when theta equals pi over 2. But pi over 2, that's 90 degrees. Right? That's 90 degrees. So in other words, what this is telling me is the area of this triangle is maximized when, got a little messy there, when it's a right triangle. Right? So if the length of the two sides stay fixed, the area is maximized when the triangle is a right triangle. Okay, so what's next? Well, I've got one more optimization problem that I want to talk about. This is it's a very practical problem. It's called economic lot size. And what makes it interesting is that there's multiple parameters involved. The situation is, you know from past experience that you're going to have a certain number of units that you need to manufacture over the course of a year. And on the one hand, there's a cost to reconfigure your plant to manufacture those parts because you make different kinds. And on the other side, there's a cost to store those parts. So you don't want to just go in on day one and produce all of your parts for a year because it's going to be expensive to store them. But on the other hand, you don't want to just produce a daily batch because that's going to drive up your configuration costs of the factory. How can we play these two needs off against each other to find, again, what's called the economic lot size, the optimal production level that achieves the competing goals of minimizing your storage costs and at the same time minimizing your configuration costs?